we're entering into a new part of the course, which means it's time for a new idea. But actually, it's not so much a new idea, it's just sort of another variation on a theme that we've been seeing again and again. Namely, we've been doing the following. We have a differential equation problem that we need to solve. And so we'd like to go from here to there. Say, well, how do we do it? Well, what we'll do is we'll turn it into an algebra problem. So in other words, instead of going directly, we're going to go around. So that is, we take our differential equation problem, turn into an algebra problem, use our wonderful honed skills in solving algebra problems to solve that, and then finally get back to our solution that we're after. So the difference is, how do we turn our differential equation problem into an algebra problem? And this is done by something that we're going to call the Laplace transform. And it's written down here. So what is it? Well, we'll write again. So the idea is you have this fancy L for Laplace. The Laplace transform of a function f of t is the integral 0 to infinity e to the minus st f of t dt. So, in other words, what happens is whatever you plug in to your function, you put it here in the integral. Now, what's coming out? What kind of object is it? Well, you think integral, so you're thinking, number, right? Because it's a definite integral. But actually, you see how there's this s. The integral depends on your choice of s. So what's happening is it's actually a new function, a function of s. And we say, all right, great. So what can we think of this as? Well, what we can think of this as, the fancy name is operator, but really it's the same thing we've seen many times before, which is we have our machine. Now what's going to happen with this machine? Well, this machine is called Laplace transform. And what you do is you feed something into the machine. So you say, all right, I feed in a function. And the machine spins its wheels, runs its computations, and says, aha, here you go. Here's a different function. Different, but related. I say, brilliant, wonderful. Now, the question is, of course, what can we do with it? As of right now, your initial reaction is like, okay, why? Well, we'll see that actually that this function has some really cool properties. And also that a lot of the things that we've been doing that relate to differential equations turn into algebra as we feed it through the machine. So that's why we have differential equations problems becoming algebra problems. And over the course of the next several lectures, we'll see how that evolves. You might also ask things such as, why this function, e to the minus st? Well, in some sense, it comes back to the idea of, what's our favorite function? Well, the answer is the exponential function. We love the exponential function, so it makes sense that we should have that there. Now, how are we going to actually use Laplace transform? Or in other words, how do we actually get our hands into it? Well, to do that, let's take a step back and think about, have we ever seen something like this before? A machine where you plug in a function and out comes another function. Well, we have in many cases, and there's one in particular I want to talk about. So the machine I want to remind ourselves of is very familiar. So here we have, here's our machine. We'll put D. D for derivative. So the derivative is something very similar. Or what happens? Well, in a derivative machine, you plug in a function. You say, okay, in goes a function, and what comes out? A different function. Now, we have notation for it, f prime of t, but the point is function in, function out. Same thing here, function in, function out. Now, how do you actually take derivatives? Now, you might say, well, I just do it every time. Well, wait, what's the definition of a derivative? A limit as h goes to 0? You do that all the time? Well, no, not that. I just have all these formulas memorized, and I just know how to use them. And that's the key. What does it mean to say, oh, I'm taking my formulas and I'm using them to figure out the derivative, or the related thing, the antiderivative? Well, the idea is, say, look, I have this nice big table. And what it is, it's a table of rules that I've gotten very used to. I'm so used to it, it's in my heart. I just know things like the derivative of x to the power k, x to the k minus 1, things like the chain rule, all these various things, they make it my table. And I use the table to do the derivatives. So what are we going to be doing? We're going to be using the definition to make a table. And now we're going to make a new table. It's going to be our Laplace transform table. And using our Laplace transform table, we'll be able to do the kinds of things that are related to the problems we're going to be focusing on, which is great. But now you might be worried, wait, I got to memorize another table? Well, if you work with Laplace transforms often enough, you will memorize the basics. The good news is, for the time being, we'll give you enough that you'll always be okay. You'll always have a table to reference. So, recapping, what's going to happen? So we start with the differential equation problem, and we're going to feed that differential equation problem through our Laplace transform table. And that's going to become an algebra problem. And we'll see how, as I said, over the course of the next few lectures, we solve the algebra problem. They might be thinking, what algebra problem are we actually solving? Okay, let's spoiler alert. What's the algebra problem we get to do? Well, it generally falls into the category of simplifying, and also very frequently partial fractions. Partial fractions. We've missed you. Don't worry, we'll get to do that a lot more. Okay, so we solved our algebra problem. Now, how do we go back? Well, the answer is we can do what's called the inverse Laplace. Now, unfortunately, there's not a nice formula for the inverse Laplace. But the good news is we don't need it because we have our table. And just as rules for derivatives becomes rules for integrals, we say, oh, rules for Laplace transforms become rules for what we call the inverse Laplace transforms. And so our table is going to be a very useful tool. So learn to use our table. That's our goal. That's our goal. Well, let's talk a little bit more about some various things we can say about Laplace transforms. So some of the things we can say is that it works really well for the kind of functions we've been talking about frequently. So in other words, exponential functions, sine cosine functions, powers of t. It doesn't work well for things which grow very quickly or blow up. So, like tangent, completely off the table. But don't worry, we're only going to focus on things where we actually have a chance of success. Another thing to say is Laplace transforms are built off of an integral. And integrals are nice, so we inherit properties. One of the most important properties that we like is that we can break up over addition and pull constants in and out as needed. In other words, it's linear. So remember that we have the Laplace transform of f of t, by definition, is the integral 0 to infinity of our e to the minus st f of t dt. Now that's just the definition. So what happens if we come in and do this combination? Let's run it. Well, we'd have the Laplace transform, constant 1 f of t plus constant 2 g of t. All right, 0 to infinity, e to the minus st times constant 1 f of t plus constant 2 g of t dt. Right? Because what's the rule? The rule is whatever's here goes there. All right. Well, now we can distribute. Say, hey, wait a second. This is integral 0 to infinity of, I'll write as c1 e to the minus st f of t plus c2 e to the minus st g of t, and all right, dt on the end. Now we have a plus. Integration can break up over addition, and we can pull out constants in each piece. So we get our constant 1, integral 0 to infinity, e to the minus st f of t dt, plus constant 2, integral 0 to infinity, e to the minus st g of t dt. And our great aha, we have that it is what we think it should be. And so Laplace transforms are linear, which means they're nice. The same thing will also hold for inverse Laplace transforms. Since Laplace transforms are linear, inverse Laplace transforms are linear. All right, well that's good. Now another thing is, when we do integration, we can always break it up into pieces. And in other words, we can do our integration piecewise. So we can also do Laplace transforms piecewise, which means this works great for piecewise functions. And indeed, one of the strengths of the Laplace transform that we're going to see in the near future is that it works wonderfully well for functions which are piecewise functions. Previously, we could handle them, but the mechanism for handling it was to say, okay, solve it for one piece, run it to the end, start the next piece over using the end, run that, and repeat, repeat, repeat. It was not good. The beautiful thing is the Laplace transform machinery will do it automatically, and it is marvelous. And it is amazing. So that's great news for us. There's another fact here, which we don't need to worry too much about, but just says Laplace transforms, there's no surprises. The only way that we can have two things match, if they're continuous, is if the original things match. So there's some sort of uniqueness in some sense. Now, we already mentioned inverse Laplace, and again, the way we're going to do it is we're going to learn our Laplace rules and say, hey, Laplace rules become inverse Laplace rules. So that's going to be an important thing for us. One more thing on our bullet point here is if we do have something is the Laplace transform of f of t, then as s goes to infinity, the f of s goes to 0. Well, why is that? Well, just think about what's happening. As you plug in larger and larger values for s, e to the minus st is going down. So it's going to 0. So this is essentially 0, is how you should think of it for large values of s. And the integral of 0 is 0. So that's the idea. And we will use that for one of my favorite facts that we can get from Laplace transforms. And I'm really excited. And you're like, if I see Steve excited, I just know what's coming. Yes, you know what's coming. We're still going to, wow, it's going to be amazing. All right, so, okay, wonderful, wonderful stuff for us to talk about. Now, I want to leave with one more piece of advice before we start going into our rule building, our table building, if you will. We use s as our new variable. Inevitably, students run into a challenge with the letter s. And what is the challenge? Well, it turns out that a lot of people write their s's very similar to their 5's. So, know how to distinguish the two. In other words, distinguish your s and your 5. And inevitably, at some point, someone will say, oh, I see a 2s. Oh, that's 25. Or they'll see a 25 and say, oh, that's 2s. And so be careful. Keep track of things. Be able to read your own handwriting. I know that sounds easy. It's not. It's actually pretty challenging. So, all right, that's a piece of advice so that you don't lose any silly points. If we lose points, we're going to earn those lost points by doing stuff that's wild and crazy, not just a simple, I can't read my own handwriting. All right, on to our rules. So our first rule, find the Laplace transform of the function e to the ct. Now notice we have c in here as a parameter, so that way we can just do them all at once, right? We're going to do e to the t, e to the 2t, e to the 17t, e to the negative 5t, all at once. Say, okay, great. All right, so how do we do it? Well, we don't have any rules yet. And when you don't have a rule that applies, or even if you don't have a rule, then you say, go back to the definition. So we say, all right, that's no problem for us. We know our definition. So we say, all right, by our definition, the Laplace transform of e to the ct is, well, the integral 0 to infinity of e to the minus st e to the ct dt. Now I just want to emphasize what's going on here is that we're plugging in our e to the ct. So that's coming into there. Okay, good. Now, well, we work on the integral. So this becomes integral 0 to infinity. Well, we can combine, right? We have e to the something times e to the something, and we say, well, their powers combined. So e to the minus st, and here you add, not multiply, add, and you say, all right, and so integral 0 to infinity of e, and we'll write this as minus s plus c times t. Now let's talk a little bit about our symbols here. We have a lot of letters. C is a constant, a parameter, if you will. Now s, we've talked about how the Laplace transform is beginning to become a function of s. So you might say, well, is s a variable? Well, yes and no. Not at this stage, because what are we doing? We're integrating with respect to t. And as we integrate with respect to t, how do we handle our non-t items? Well, we handle them like constants. So we're going to think of s and c both as constants at this point in time. We say, all right, well, we have e, constant t. Okay, well, we know how to handle that. We say, all right, wonderful. This will be e to the minus s plus c t, and then you divide by the constant. So that's minus s plus c. And evaluate 0 to infinity. Okay, so we're almost done, except we have our first What's our Well, there's a small issue, and I want to talk about this because I want to make sure we have this in our mindset going forward. Our small issue is the following. If we look at this exponent, we're plugging in t as infinity. Now, what this is in front makes a difference. Because, well, if the part in front is a positive, then we're blowing up. If the part in front is negative, we're collapsing to 0. So we'd like it to be negative. But now we're like, well, it kind of depends on how s is related to c. So there's some technicalities, but here's the rule of thumb. We're not going to stress about that part. So, rule of thumb number 1. And, okay, well, you always know when someone says number 1, there should be a number 2, but we'll get to that in a second. Assume s is large. And when I say large enough for what you need. So say, look, since s can vary, we'll assume it's so big, it's bigger than c, so that this is negative. Okay. And just make that your rule of thumb going forward, and don't worry about it. And everything will work out. All right. So at this point, we're like, cool. Now, when we plug in infinity, we know that s is large, so this is negative. So we have e to a large negative, which means 0. So we get 0. Subtract e to the 0, 1. So 1 over negative s plus c, which is 1 over s minus c. All right, nice. So recapping our rule that we have right now, we can say the Laplace transform of e to the ct is 1 over s minus c. We can do a special case here. Our special case, well, we can do it for any value of c, and a nice value of c is 0. E to the 0, 1. So, say, look, Laplace transform of 1, well, plug in c equals 0, plug in c equals 0. 1 over s. All right, good. Good, see, our table has started. Wonderful. Now, right now, these kinds of rules are our basic building blocks. It's like we have a collection of functions, and we're going to work with the functions. Well, there are other rules that we'll build up. That'll be part of our table, and that's our next task. But let me give you rule of thumb number 2. And this is something to keep in mind, and oftentimes this will not be something we worry too much about, but I just want to emphasize it now. So we said, okay, assume s is large enough. There's another thing we can say. We only care about f of t for t greater than or equal to 0. Now, why is that? Well, because, go back to the definition of Laplace transform. Your integral goes from 0 to infinity. So what happens before 0 has no bearing on the Laplace transform. None. Nothing. And so if your function f of t is doing crazy stuff for negative values of t, whatever, we don't care. We only care what happens to f when t is greater than or equal to 0. All right, good. Well, let's keep making more rules. So let's do the following. If the Laplace transform of f of t is some function f of s, then find the Laplace transform of e to the ct times f of t. All right, well, let's think about what's happening here. What can we say? Well, first off, what does it mean to say the Laplace transform of f of t is f of s? Well, that says that f of s is integral 0 to infinity of e to the minus st and f of t dt. So that's, remember that. And now we're going to say, okay, let's work with this. Now we don't have very much going for us. Now if f of t was 1, it's like, hey, we know how to do that. Sure, great. But that's just one case. This is for like any f. So it's like, well, so okay, what do? We go back to our rules. We always go back to our rules. So the Laplace transform, e to the ct f of t, definition, integral 0 to infinity, e to the minus st, e to the ct f t dt. Okay, right? Because we're saying, look, this is our function that we're plugging into our Laplace transform, and you just put it in. All right. Well, now we'll just channel what we did in our last rule. Say, hey, we have these two exponential functions. We love exponential functions. We know how to work with them. Let's put them together. And we say, all right, well, if we do that, well, we'll have 0 to infinity, e to the minus st plus ct f of t dt. All right, and we'll say integral 0 to infinity e, and I'm going to write this as pull out the t and pull out the minus. So we have s, and here's the fun part, pulling a minus out of a plus leaves us with a minus c. All right, now here we go. We stare at this for a moment until something occurs to us. Well, hopefully we don't have to stare too long. And we're like, because we say, these things look very similar. We have our bounds are matching, our f of t dt is matching, and the only difference is here it's the minus st, here it's minus s minus ct. So in particular, where you see s here, you see s minus c there. You say, what? Wait, that means this is the same thing, because see, I can imagine plugging s in. So I was like, oh, it's like f, but instead of plugging s in, we plug in s minus c. And that's our rule. Cool. All right, so let's write this down. And this is going to be a really important rule. And we're going to use it a lot. So we want to be sure we can just be like, yes, I recognize this rule. And what does it say? Well, what it says is on the left-hand side, multiplying by an exponential before you take the Laplace transform corresponds to a shift in the after you take the Laplace transform. So multiplying by an exponential becomes a shift, and that's our punchline. So, okay, cool. And so we'll actually use this rule quite a lot. So multiplying by exponential, I'm just writing this down so I remember it, because, you know, I like to remember things. And then here we have a shift. And the amount we shift corresponds with what's up here in the exponential. So, all right, great. This is a really nice rule. And this is one of our gluing rules, right? I talked about how you have your building blocks, which are some functions, but then you have ways to start combining functions. And in particular, we say, oh, it's really easy to combine an exponential function with any other function. Because it says, if you know how that function behaves, and there's an exponential, just figure out this function and then shift. All right, good. More rules. Let's go and do some more rules. So we've done the exponential function, sines and cosines. Let's tackle that. And we can handle that by saying, well, wait a second, sines and cosines really aren't that different from the exponential function. In fact, they're related to each other. And there's this wonderful fact. And it kind of tells you here, e to the I bt. Well, what is e to the power I bt? Well, whenever you have a complex upstairs, it becomes sines and cosines. So this is cosine of bt plus I sine bt. All right, well, let's start. Where can we start? Well, it says use the Laplace transform of e to the I bt. Now you might say, well, we have a rule for that. Let's write our rule down just so we have it for reference. Laplace transform of e to the ct is 1 over s minus c. All right, so we can say, hey, that means that the Laplace transform of e to the I bt, we can run that. That's equal to 1 over s minus ib. Now this one you might say, whoa, hold on. That was for c a constant. Yeah, that's right. That is for c a constant. What about ib? That's a constant. You know, you might say, but wait, isn't that complex? Right. We never said that c had to be real. And indeed, it works for any complex value for c. All right, well, that's good. Now, at this point, you're probably thinking, how does this give us our answer? Well, let's work on both sides. Let's start with the right-hand side. Right now, we have 1 over s minus ib. I don't like complex numbers in the denominator. It's hard for it to see what's going on. So we want to sort of clean the denominator up. So what can you do to get rid of a complex number downstairs? Is there some algebra? Well, of course there is, right? Our class feels like an algebra class. And so what is it? Well, it's what we call multiplying by the conjugate. So s minus ib, s plus ib. All right, well, that's great. So what would this be? Well, upstairs you get s plus ib, because 1 times that. Now here you have something minus something, something plus something. And if you remember, if you FOIL, okay, s squared. SIB minus SIB cancels. Then you have this minus I squared B squared. But since I squared is a negative, that ends up with a plus B squared. Okay, or we can separate. Now the nice thing is we've moved the complex part upstairs, and separating upstairs is easy. We're going to take advantage of something called the plus sign. And in other words, we can pull things apart upstairs very simply. When it's downstairs, work. And we'll come back and revisit that in the near future. So we have S over S squared plus B squared, and then I B over S squared plus B squared. All right, so we'll stop there on that track, and we're going to come back this way. All right, now what can we do? Well, we can say, look, I know what e to the IBT is. So we say, okay, well, this is the Laplace transform of cosine bt plus I sine bt. All right, because I'm just saying these are equal. Now we use the fact that Laplace is nice, linear. You can break up over addition and pull out constants. I is a constant, so we can pull that constant out. So I say, okay, so this is the same as the Laplace transform of cosine bt plus I Laplace transform of sine bt. And now what can we do? Well, we say, well, look, real recognizes real, right? Because these things are equal. And we say, well, okay, so that says that the Laplace transform of cosine bt, that's the real thing. That matches up with our real thing over here. And by a similar argument, we say, hey, the imaginary part, which is the Laplace transform of sine bt, that matches up with our imaginary part over there. So our two new rules, two for the price of one, bargain. How nice. We have that the Laplace transform of cosine bt is s over s squared plus b squared, and the Laplace transform of sine bt, that's equal to b over s squared plus b squared. And there we go. Nice. Cool. We're making great progress. We have exponentials, sines, and cosines, and life is good. However, you might be a little bit suspicious about this. One, you think this is really beautiful, but you're complex. It's just people don't feel comfortable with that, even though a lot of what you've learned in calculus actually works just as well for complex as it does for your normal real numbers. So I'll show you another way that you can get to cosine and sine. So if you dig through your old Calc 2 notes, Calc 2, what a glorious time. A wonderful, exciting class. You'll discover that we did something where we did integration by parts twice, and then sort of rearranged to figure out how do you integrate something like e to the at sine bt or e to the at cosine bt, and we have these expressions. Well, good thing we wrote it down so we didn't have to rederive it. Say, okay, great. Now that we have that, how can we use it? Well, suppose we wanted to find the Laplace transform of sine bt. We'll start there. So what do? Well, the Laplace transform of sine bt, by definition, we say throw it in. Integral 0 to infinity of e to the minus st. And all right, now put in your function sine of bt dt. And you say, oh, well, I have this expression. So what we'll do is we'll use this expression. The only thing we have to change is that instead of an a, we have minus s. So you say, okay, so according to the rules, this would be minus s over s squared plus b squared e to the minus st sine bt minus b over s squared plus b squared e to the minus st cosine bt, and evaluate 0 to infinity. All right, well, now at infinity, the exponential terms push you down to 0. Okay, so we get 0. Subtract. Now, when you plug in 0, sine of 0 is 0. So that part goes away. So you're going to have 0 minus, well, here you have b over s squared plus b squared. E to the 0 and cosine of 0 are 1. And we end up with b over s squared plus b squared. Same as before. Same as before. But now you're like, okay, great. No complex stuff involved, given that we had to derive the formula, which, granted, that can feel complex. For completeness, let's go ahead and do the other one. Okay, so Laplace transform of cosine bt, similar way, integral 0 to infinity e to the minus st cosine bt dt. So we use our formula, but everywhere there you see an a, so for example over there, put in minus s. All right, so that would be equal to, well, we have b over s squared plus b squared, and then that's e to the minus st sine bt, and then here minus s over s squared plus b squared e to the minus st cosine bt, and go from 0 to infinity. Again at infinity, your exponential terms drive you to 0, so we get 0. Subtract. When you plug in sine of 0, you get 0. And then we have the s over s squared plus b squared. E to the 0 and cosine of 0 are again 1. So yes, it is what we claim. Whew, good. So now, no doubts. We definitely know how to do sine and cosine. All right, so where are we at? We've done exponential, sine, cosine, powers of t. Let's talk about that one. So it turns out that there's this really interesting function called the gamma function. And it's denoted with a gamma. So that's the Greek letter gamma, capital gamma. And it's frequently used in mathematics. And how is it defined? Well, it's going to sound familiar. The integral from 0 to infinity, e to the minus t, t to the power x minus 1 dt. Like, oh, that does sound really familiar. Yeah, it has a kind of the same flavor, if you will, of our Laplace transform. So, okay, all right. Well, what are some things that are known? Well, we can do a couple of really easy facts, which is that gamma of 1, right? Because what happens? 1 to the minus 1, 0. So that's just, cover that part up. E to the minus t. And you can compute that. And so gamma of 1 is 1. Okay, cool. What about other numbers? Well, here's where it starts getting weird. For whole numbers, we're going to see it's nice. For fractional numbers, you get strange things. And in particular, gamma of a half is square root pi. And if that makes you say, huh, you're right, huh. But it's true. It's true. And indeed, using tools that you learned in multivariable calculus, you can actually establish that. We don't need to worry about why it's true. For right now, we'll just say, okay, it's true. And so, and besides that, other numbers are just weird. So let's just say you only need to worry about whole numbers or a half, which is good. Good news for us. So we say, okay, well, how can we use this? Well, we want to use the gamma function to do Laplace transforms. And there's three things we're going to do here. All right, so let's start with our various rules. Okay, so the first thing it says, hey, show a Laplace transform of t to any power is related to our gamma function. Okay, all right. Now, it started the process for us, right? Because what do you see here? This part is the definition of the Laplace transform. So you say, okay, so let's start with this integral. All right. So we have our integral 0 to infinity e to the minus st t to the a dt. Now we start by staring at these two. Say, okay, how are these similar? How are they different? Well, a big thing is the exponential here. It's e to the minus t. Over here, it's e to the minus st. So what can we do? Well, we want to turn st into just t. How does one do that? Well, we reach back and we say, we have good rules. And one of our good rules is called substitution. So we're going to say, let's let tau equal s times t. And if we do that, we can say then that d tau is s dt. All right? So substitution. It's a great way to change your name and fix the inside. So right now, the st, that's our inside that we're trying to fix. So let's see what happens. Well, with our bounds, what do we get? Well, we're going to get integral, and well, t equals 0. 0 times s is 0. As t goes to infinity, s times infinity, infinity, great. E to the minus st, e to the minus tau, cool, cool, cool. Well, what about t? Now t, well, you can look at this and say, look, t is really tau over s. So you say, oh, okay, so this is tau over s to the power a. And finally, how do we handle that dt? Well, again, there's this s, move it across, 1 over s d tau. Okay, so those two are equal to each other. Okay, well, let's clean this up. We have an s to the a downstairs. We have another s, and notice that we're integrating with respect to tau. So s is still a constant. So we have a total of a plus 1 s's downstairs. We can pull them out of our integral. So this is 1 over s to the power a plus 1. Again, a and 1. And then what's left? Integral 0 to infinity. And then we'll have e to the minus tau, and then tau to the a d tau. And now we say, oh, okay, let's compare. 0 to infinity, good. E to the minus tau, great. Tau to the a versus tau to the x minus 1 d tau. So we say, oh, this is the same as this expression, where what we've done is we said, okay, this is our a. Well, if x minus 1 equals a, what is x? The answer is a plus 1. So we say, okay, so this is gamma of a plus 1. That's the integral over s to the power a plus 1. All right. And good. Okay, so we've satisfied our first bullet point. So now we know what we look like. Now, the punchline here is gamma is a number. So if we're dealing with t to the power a, we know it's going to look like s to the power a plus 1 downstairs. And it's just saying, okay, what's that number upstairs? Well, let's talk about that. So the next thing we're asked to do is to say, well, this gamma, let's take a look at some properties. gamma of x plus 1 versus x gamma x. Okay. Well, let's try this out. So by definition, gamma of x plus 1 is integral 0 to infinity e to the minus t, t to the x plus 1 minus 1, which is just t to the x, dt. Now we're trying to get to gamma x, which has an x minus 1. So we say, okay, how can I make t to the power x look like t to the power x minus 1? We could take a derivative. Yes. But how might we do that? Oh, we have ways, and namely integration by parts. So we'll say, look, if you let this part be the u, and then we'll let this part be our dv, we'll see that v, well, the integral of e to the minus t is very straightforward. It's minus e to the minus t. And our du is xt to the x minus 1, right? Power comes down. That's where the x is coming from. T, and subtract 1 from the power. So this is equal to, what do we have? Well, we have uv, so minus t to the x e to the minus t, subtract the integral of v du. And I should point out this is definite integral, so we need to evaluate. We'll come to that in just a second. Integral 0 to infinity v du, which will be, oh, whoops, got my dt there. Classic mistake, but that's all right. We can always fix our mistakes. That's the nice thing. In life, we can fix our mistakes. It's easier when you catch them sooner. So catch your mistakes as soon as you can. All right, v du, so minus e to the minus t. And then we have our xt to the x minus 1 dt. Now, let's talk about our bounds here. At infinity, the exponential function wins. Exponential always trumps polynomial. And so we say, okay, we're going to go to 0. When you plug in 0, well, e to 0 is 1, but 0 to a power is 0. So the whole point here is that this part goes to 0. Now, what about the other part? Well, minus a minus, plus, and then x is a constant. So go ahead and pull it out. So you have x integral 0 to infinity e to the minus t, t x minus 1. And then I say, whoa, that feels really familiar. Yeah, it's what we have up here. So that is our x gamma x. So good. Now, at this point, I should pause and say, why do we want the gamma function? What is it about the gamma function that makes us say, gamma, you're awesome, woo! We like the gamma function because it has this relationship. And in particular, what we're going to show in the third point, so hold on just a second. In our third point, we're going to say, hey, this behaves like factorial. So that's why we like the gamma function. It's behaving like a factorial, but it works for all numbers, not just whole numbers. Okay, so our final point. Suppose we have a whole number. What's the Laplace transform of t to the n? Well, we know from part A, well, we can say, look, the Laplace transform of t to the n is this expression, gamma n plus 1 over s to the n plus 1. Like, okay, great. What's gamma n plus 1? So here, let's do a computation. So gamma of n plus 1, we come here. Well, we say, look, that says reduce it by 1, we're down to n. And then you say n gamma n, right? So whatever is inside, go down by 1, that number gamma that number. So, okay, well, here we have n. So again, apply the rule, n minus 1 gamma n minus 1. So this is the same rule, only now for the x equals n minus 1. Okay, well, do it again. n minus 1, whoops, sorry, 1, n minus 2, gamma, n minus 2, and dot, 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 which is mathematical shorthand for the pattern continues until we get to a point all the way where we've gotten to 2 times 1 times gamma of 1. But what do we know about gamma of 1? It's 1. Okay, so this is 1. What about all of this? N times n minus 1 times n minus 2. It's n factorial. Or as you might say, n, right? Because, exclamation, like, n. Yes, it's n factorial. Cool. So our answer is n factorial over s to the power n plus 1. Nice, nice. All right, well, good. Lots of rules, lots of rules. So here we have another rule. So maybe let's take a moment and see what else we can say. Let's find the following. The Laplace transform of e to the ct sine bt, Laplace transform of e to the ct cosine bt, and the Laplace transform of e to the ct t to the power a. Now you might be saying like, whoa, that's asking quite a lot. Well, it is, but we have rules, right? So let's write down our rules. We have 4 rules that we can point to, namely the Laplace transform of sine. Well, sine is b over s squared plus b squared. The Laplace transform of cosine, and that's s over s squared plus b squared. And the Laplace transform of t to the a is gamma a plus 1 over s to the a plus 1. And then there's another rule. The Laplace transform of e to the ct f of t is what? Well, it's f of s minus c. So we have 3 building block rules and sort of 1 gluing rule. So these are just like, okay, we know particular functions, and this says, oh, what happens when you combine with an exponential? So what's the punchline? The punchline is, when we combine with an exponential, we shift. We shift by what's up in that exponent. So we can actually just use the rules now and say, okay, if we combine the sine with this e to the ct, you say, all right, so what we're going to do is say that the Laplace transform of e to the ct sine of bt, well, that would be what? You start with the Laplace transform of the sine, but now you shift. So everywhere you see an s, you put s minus c. All right, great, done. See, we're not rederiving things. This is all table work at this point. Use the table. And so we have a surprising amount of our table already done. So there's still some more things, but a lot of the hard ones are done. E to the ct cosine bt. Again, we know how to handle just cosine. And then we say, now shift. So everywhere where you see an s becomes s minus c. So s minus c over s minus c squared plus b squared. And here, again, Laplace transform of e to the ct t to the a is, well, we're going to have a shift by s minus c. So the only place where you see an s is downstairs. So the upstairs is still gamma a plus 1, s minus c to the power a plus 1. All right. See, isn't that great? It's nice to have our table, because the better our table is, the quicker we can do things. It's always nice to be able to say, oh, I can combine a few facts on the table and done. I don't have to use the definition. And in general, it's good to avoid the definition if you can. So here we are. Finally, what have we done? We talked about our table. This is our table for today. What have we established? Well, we have our nice rule about shifting, and then we have a collections of basic functions. Now, the thing is, we're not going to put down everything on our table because, of course, if we try to write down everything, that's too much. We're going to write down the key things. So we tend to focus on basic functions. The exponential function, the powers of t, sines, cosines, but things like combinations, we say, oh, use your rules. So that's the start of our table. It'll grow and grow and grow. So keep coming back and we'll see it grow. See you again.